Hello, everybody. Good afternoon. Welcome to this webinar. I hope you hear me fine because it seems there are some issues with the connection. So my name is Irene Verri, and I am the moderator of this virtual conference, the first of a series on the technologies developed by the Bamboo Project. Today we are going to hear about waste heat recovery as a solution to boost efficiency in energy-intensive industries. So first of all, for a better experience, let me remind you a couple of rules. Please keep your microphones and cameras switched off so that we can focus on the speakers and the slides. And if you wish to ask questions, just write them down in the chat box, which you should see on the right side of your screen. I also inform you that this webinar is being recorded, so it will be possible to access it in the future. So this is what is going to happen in the next hour and a half. After this introduction and a few polls for the audience, Jorge Arroyo and Álvaro Pecharroman from Fundación Circe will introduce us to the Bamboo Project, its objectives and the technologies it proposes. Then Tommaso Ferrari and Mirko Ferrari from Turboden, will illustrate the topic of this webinar, which is, as we said, waste heat recovery as a solution to boost efficiency in energy-intensive industries. Now, before delving into the topic of this webinar, we wish to ask a few questions to you, the audience, to learn a little bit about you. So we are going to propose a few polls that you are invited to answer. These will give us an idea of who we are talking to, what kind of, can I say, expertise you have on the topic. If Veronica can send the first polls. Okay. So the first one is a bit personal. What do you expect from the webinar? So let us know. You should be able to vote. And then we'll give you the results. So you can learn a number of things from this webinar, or you could try to network with companies and share similarities and solutions. Okay. Okay, so these are the results. The majority expects to learn about efficient technologies for their company, then learning about projects of similar companies. Third place, networking with companies and share similarities and solutions. And last, learning about standards and regulations. Okay, let's pass to the following poll. We ask you to select your area of work, which might be a number of them: paper industry, steel and iron industry, mineral industry, petrochemical industry, or other. Okay, so these are the results. Most of you are from other, which is a very large industry, apparently. Then there is a petrochemical industry, which is not surprising. Then steel and iron industry, paper industry, and mineral industry. Okay. Next, we would like to know what is your role inside your industry. So R&D, technician, maintenance, management, or other. All these questions, of course, are also to help us. I mean, they can help us understand better our audience and orient us for the future webinars. So we discovered that most of you are managers. Then there are other functions, other roles. At 19%, we have R&D and technician, and then there's maintenance. So now let's pass to something more about your knowledge of the topics of this webinar. So is it the first time you hear about organic Rankine cycle technology? It will be interesting to see if there are people like me who have never heard of it, but I am not in the industry since I am a journalist, and those who know about it, how they learned about it. Yes, is at 23%. So it's not many, but it's not very few either. Most of you have already done studies or researches in the past. Interesting. Some of you have seen ORC plants in operation at industrial scale. Nice. And a little bit of you, just 3%, have seen ORC technology in operation at lab scale. Now let's test a bit your knowledge about the topic. There is no real right answer, the panelists told me, but it's interesting to see what you know, what your experience is. So what applications are most suitable for RC power plants? What do you think? Okay, for most of you, well, 47%, so it's a relative majority, all of the above. So all these applications, followed by waste heat recovery, biomass, and geothermal. Maybe we could hear from our panelists if there is a better answer. Maybe Jorge or Alvaro. No?
No, I think that our colleagues of Turbo then can be replied more accurately.
Yes.
Okay.
Right. Just a quick comment on this, since we are asked. So actually, all these applications are suitable for organic ranking cycle application, and we will see this in a few minutes during our presentation.
Okay, great. So let's go through the next poll. What is the typical ORC plant capacity? So electric power production. Let us know what you think. Okay, so you can see the results here, and so I think we will discover more in the presentation. Let's leave a little bit of suspense, maybe. And last poll. What is the levelized cost of energy that you expect from a waste heat to power project based on ORC technology? And here are the results. Okay, have a look at it. And thank you everybody for your participation. Now I will give the floor to the first panelist.
Jorge and Alvaro from Circe.
Jorge Arroyo and Alvaro Pecharroman from Fundación Circe, who will tell us more about the organizers of this webinar series, the Bamboo Project. I think Jorge is the first to speak. I ask so the other panelists keep their cameras and microphones off. So please, Jorge, tell us about this project.
Okay, thank you for the introduction. Good afternoon, everybody. We will have a presentation, a brief introduction about the Bamboo project, which is coordinated by Circe. And today we are here, Alvaro Pecharroman, which is the project manager, and myself. I am the technical coordinator of the project.
Okay, so first of all, thank you very much to everyone for joining the first of the webinar series. Then you're gonna have a little more explanation about the rest of the interesting webinar that we wanna be developing in November. So what is Bamboo? Bamboo is an innovation action that are included in the goal for the AIDS 2020. They have a funding from the UN, about 11-10 million euros. The duration of the Bamboo project is 54 months, and we are near to the final. So we think that is very interesting that show to the rest of the community the learning that we have in the during the project. Okay, and the consortium is coordinated by Circe, as Jorge said before, and we have 19 partners. Some of them are technologic centers, and we have as well a lot of private companies that are working with the demos of this project. And follow, we have Jorge that gonna tell us more about the technical part of the project. Thank you very much, and enjoy the webinar.
Thanks, Alvaro. Most of you know, the energy transition towards a secure, competitive, and decarbonized energy system is a challenge for the intensive industries in the European Union. In this context, Bamboo is developing new technologies which will help to reduce the energy costs between a 15 to 20%, reduce the greenhouse emission up to 23%, and improve the energy efficiency to the 20%. In this sense, Bamboo project is aimed at demonstrating innovative technologies that can contribute to the European industry decarbonization, based on the three main pillars of the project: the waste heat recovery, the electrical flexibility, and the waste stream valorization. In Bamboo, we are working on the demonstration of these technologies at an industrial level in the steel, petrochemical, paper, and mineral sectors. In Bamboo, we demonstrate technologies for waste heat recovery. This is to valorize energy content of some waste stream, which has some energy associated to their temperature. The project aims at demonstrating two main technologies: high temperatures heat pumps and ORC, Organic Rankine Cycles. In the case of the high temperatures heat pumps, they are active system that allows upgrading low to medium waste streams to higher temperatures. In the particular application developed in the case of ArcelorMittal from the steel sector, we are producing steams which can be used in other parts of the process. This application is expected to have a direct impact on the fossil fuel consumption of the plant, since part of the fuel used to generate steam is replaced by the steam generated by the heat pump. In the case of the petrochemical sector, the technology studied is the ORC, which will help to reduce the electricity consumption of the Tüpraş refinery in Turkey. In this case, the ORC is analyzed to recover medium-grade waste heat generated in a crude distillation unit, and it's used to produce electricity which can be consumed inside the plant, helping to reduce the electricity bill of the plant. In the second pillar is the electrical flexibility, which includes technologies and operational strategies that will make it possible that some industries benefit of lower electricity prices and provide grid services, as well as enabling the integration of renewable energy. In this case, Bamboo is working in applying this concept in the pulp and paper sector, where different strategies and technologies are implemented to allow the operation of a paper plant as a battery in a regional power grid. In this case, the concept means that during summer, where it's a high share of renewable energy, especially photovoltaic energy, is expected, the plant will reduce or shut down their own generation system to consume power of the grid. In winter mode, when there is low renewable energy generation, UPM's generation system can be used not only for internal use, but also to supply some energy to the local grid. In the third pillar, which is the waste stream valorizations, we analyze technologies and processes that allow the upgrading and valorization of different waste streams which have some calorific value and can be used as fuel in other parts of the processes. Here, Bamboo aims at demonstrating different technologies in the steel sector and the mineral sector. In the case of the steel sectors, The concept is to increase the valorization of some of processed gases as fuels to increase the efficiency of the plant and reduce the fossil fuel dependence. We are applying two technologies to contribute to the valorization of these gases. On the one hand, CFD simulation allows simulate and analyze the behavior of these fuels when used in some combustion equipment, and we are also developing a novel flame monitoring system for the monitoring of the combustion for efficiency and emissions improvement. In the case of the mineral sector, we are working on the replacement of coke by biomass with a direct impact on the dependence of the fossil fuel of the plant of Grecian magnesite. Here, CFD simulations have again a very important role, together with the development of a multi-fuel low NOx burner, which has been developed to introduce biomass as fuel, contributing to the reduction of CO2 emissions and the fossil fuel consumption. This slide is a brief summary of the indirect potential impact based on the application of the combination of the bamboo technologies to the 1% of the industries of each sector involved in the bamboo project. You can see the reduction, the most important reduction could be in the case of the steel and iron sector, where a drop of 212 million of kilowatts per hour per year and savings and 10 million of euros in fuel, direct savings in fuel consumption, and 160,000 tons of CO2. You can also see here the important reduction in these indicators for the rest of the cases. Finally, I would like to remind you that this is the Bamboo Industry Month, when we are carrying out some webinars to show and to demonstrate these technologies, starting off today's webinar. So I encourage you to register to the next webinar, and if you can't attend, you will have the webinar uploaded to the YouTube. So I encourage you to go to it. So thank you for attending today. If you have some doubts of the project, you can go to the webpage of the Bamboo project or contact directly to Alvaro or myself. And I hope you find today a webinar of interest. Thank you.
Thanks a lot, Jorge and Alvaro, of course. All these topics look really, really interesting. And I would like to, I look forward to hearing more about all of them. But I would like to ask you first a little question before we delve into the topic of today's webinar. Since we are at the end of this project, can you tell us if there have been some challenges, some challenges, some obstacles that you have overcome and or that you are overcoming?
Yes, this was a very challenging project because, as everyone knows, we have to fight with the pandemic. As we make a real demonstration in sites, this was very complicated to finalize all the necessary previous work to have the demos in the sites of the industries. So I think that was one of the most challenging, but we managed currently, and fortunately we have a good result to show by the end of the project. And we think that this can be a good principle to have a new project that can take advantage of our learning and our knowledge of this technology.
Thanks a lot. So let's get into the topic of today's webinar, waste heat recovery as a solution to boost efficiency in energy-intensive industries. I remind you that you can send your questions in the chat box, by the way, and we will answer at the end of the session. So I give the floor to Tommaso Ferrari and Mirko Ferrari from Turboden.
Hello and good afternoon, everyone. I hope you can hear me well. Let me first thank Fondazione Circe as well as Icons for, let's say, having, hosted this first webinar about Bamboo project. It's of course a good opportunity for us to explain how organic ranking cycle technology can work in this path towards decarbonization. So today we are going to speak about waste heat recovery in energy intensive industries. We will focus on two, let's say, macro areas, basically the petrochemical sector and then other energy intensive industries such as glass, steel and cement. I will cover the first part of this presentation, and then my colleague Mirko will conclude about the, let's say, cement, glass and steel part. Just a couple of words about Turboden. I hope that many of you already know us as a company. If not, we are an Italian company, part of Mitsubishi Heavy Industries, that design and supply organic ranking cycle turbo generators for power production. The company is now more than 40 years old, and let's say in these years we started as a small engineering company, and we are now a supplier, an established supplier for organic ranking cycle plants with many references all around the world. To get started, we just want to spend a few minutes talking about the technology for those of you that are not familiar with organic ranking cycle. So the name itself tells a bit about this technology. We are talking about we are talking about heat engine, basically a ranking cycle working between a heat source and a cooling source to produce mechanical power and then, of course, electric power. The term organic stands for the type of fluid that is used within the cycle. So differently from the most famous, let's say, steam ranking cycle that uses water as a working fluid, organic ranking cycles use a variety of organic compounds as working fluid that provide some specific features to the technology itself. So here you can see schematically what the saturation curve of a typical organic ranking cycle looks like, as well as the main components of the system. Just let's say in brief, what we want to do is to take some thermal power, possibly coming from a waste resource that we have available in a certain facility, and convert this thermal power into electric power by means of this thermodynamic cycle, which is a closed loop working, as I said, between a heating source and a cooling source. The main components of the system are the ones represented here on the right of this slide. We have heat exchangers, of course. One heat exchanger receiving the thermal power from our heat source. a heat exchanger on the cooling side to reject the heat that cannot be converted into electricity. And this component is this called condenser. It has the component that condensate the organic fluid that we have. We have an internal heat exchanger that just helps exchanging internally to the system some heat that is available after expansion in the turbine. And then we have two, let's say, rotating equipment. The pump, which makes the organic fluid flow through the cycle. And of course, the turbine, which at the end produce the mechanical power that is then converted into electricity. So basically, the heat source is used to vaporize the working fluid at high pressure. This working fluid expands in the turbine. The turbine extracts the useful work that is then converted into electricity by means of an electric generator. The vapor leaving the turbine has still some energy content that can be exploited within the regenerator component, which is basically an internal heat recovery. And then we condensate our working fluid to make it back in the liquid form to restart basically the cycle with our pump. So the overall concept is fairly similar to a typical steam cycle that is maybe more famous since it has been one of the most used way to produce power in our history. So the working mechanism is similar. The main differences come from the working fluid that is used. And this main difference is actually represented here in this TS temperature entropy diagram for both water on the left side and a typical organic fluid on the right side. So as you can see, the shape of the saturation curve is fairly different. This comes directly from the property of the fluid itself, water in the case of steam cycle, and the typical organic compound in case of organic Rankine cycle. The main difference, as it is also, let's say, highlighted in the graph, is about expansion. So the segment that is represented as 0.3 to 4. So you can see how in organic Rankine cycle, this expansion always occurs in the dry vapor area of our diagram. And this means that the turbine is always operating in dry conditions, no matter what is the inlet condition of the working fluid at the inlet of the turbine itself. This specific thing comes from the type of fluids that we use as organic fluid, which have higher molecular weight compared to water, for example. But overall, this gives the advantage of having a turbine which is, let's say, more compact in terms of size, but also more simple in terms of overall management. We don't have to reach in organic Rankine cycle any specific superheating condition of the inlet vapor in order to expand it in the turbine, because we know that as long as we have vapor in the turbine, we will have vapor also at the outlet of the turbine. So there is no risk of liquid droplet formation within the turbine. The expansion will always be dry in design and in off-design conditions. And this overall simplifies a bit the management of the overall system, which at the end of the day is rather simple if compared, for example, to typical steam turbines. At the same time, let's say, and this is, let's say, one of the main advantages of organic Rankine cycle over steam. At the same time, the fact that we have a working fluid which is working in a closed loop means also that we don't have any water at site to operate this organic ranking cycle, and this might be, let's say, interesting for those applications where water supply can be, let's say, somehow problematic or maybe expensive. If we think about desert areas or areas where there is no water available. At the same time, organic ranking cycle being, let's say, a quite simple technology and having this specific feature on the turbine, let's say, brings to another important advantage, which is the very high flexibility of this thermodynamic cycle that can actually work very well both at design point as well as in off-design conditions. And this is typically a characteristic that is very appreciated when you are doing a waste heat recovery from another process, which is maybe, let's say, a production process like cement production or glass production, where you have the production process that goes by itself and does not have to follow anybody or anything else rather than the production schedule. And then you have organic ranking cycle that follows what is available in terms of thermal power that could be also discontinuous throughout time. And this chart shows you, let's say, how the two technologies compare in terms of the rating when working at partial load. So let's say compare to the nominal efficiency that you have at design point, the ORC cycle is, let's say, is working well also in off-design condition, maintaining an efficiency, a thermodynamic efficiency closer to nominal when working at partial load. So that if you see here, basically at 50% of the load, you can expect that the thermodynamic efficiency of an organic ranking cycle is 90% of the nominal efficiency of the cycle itself. Typically, this is not, let's say, reachable with a common steam cycle, considering that to avoid erosion problems in the turbine, you also want to have more defined characteristics of the water stream entering the turbine itself. So at the end of the day, organic ranking cycle technology can be defined as a simple technology where there is fully automatic operation of the unit. There is no need of a patented operator at site taking care of the steam, basically, which is instead something that is required for steam cycles. The technology is flexible. We have seen how it can work both at design and off-design conditions with very good efficiency. It is a very reliable and dependable technology. It is simple, and this also helps reaching a very high rate of availability of the plant in time. And of course, since we are, let's say, applying our technology to do waste heat recovery, or also there are other applications possible, but still in the field of renewables, it is a technology that can help targeting emission reductions and, more generally speaking, can help the path towards decarbonization. So for what concerns the type of applications that we can target, as I anticipated, maybe there are several applications that can be covered through organic ranking cycle. Historically, organic ranking cycles are associated to geothermal applications where the temperature of the heat source is rather low, we receive the brine from the underground and we want to produce power. Steam cycles suffer a bit the low temperature, so organic fluids can cover this gap basically. But at the same time, being the technology very flexible, automatic, and let's say requiring a low level of operation and maintenance, it can be used also for small power plants in the range of 1 to 3 megawatt, typically in biomass application, which is instead a rather high temperature application. Here, basically, the characteristics of simplicity, automatic operation, low O&M helps, let's say, making this technology, let's say, very interesting for this type of decentralized small-scale power plants. Same is for waste to energy, where waste in this case is, let's say, the waste from a municipality, for example, or also some animal waste that could be present in big farms, for example. We can talk about, of course, waste heat recovery in cement, glass, and steel, which will be one of the focus today, as well as waste heat recovery in the oil and gas sector. So in both cases, we are talking about waste heat recovery. We, let's say, are used to divide these two words because there are some differences in the approach in this type of application, but still we are talking about waste heat recovery, as it is actually when we talk about combined cycles. So when we have gas turbines working open cycle, what we can do is to consider an organic Rankine cycle system to close the cycle and make it a combined cycle, as it would be with the steam turbine. For this technology, let's say we have seen from the polls at the beginning of the webinar, there was a 25% of you that were not aware about this technology. So someone might wonder if it is a new technology or if, let's say, it has been around for just a few years. Well, this is not the case. Here I've taken some data from an interesting website, which is ORC World Map, which is updated up to 2017, but still gives an idea of where organic Rankine cycle has been employed in the world, and it's giving also some interesting shares about what type of application was the most common. The numbers now are, of course, a bit higher compared to the ones that we see here, but this was just to say that the ORC technology has been around for a while. It is a very well established technology used all around the world. And if we look at Turboden references, we can see how we have plants, let's say, in many places, many countries in the world, actually 50, with more than 400 ORC-based power plants installed worldwide, with these figures in terms of operating hours reached overall on our fleet, in terms of thousands of gigawatt hour of electricity produced, and average availability of our fleet. And you can see how actually this availability, which is an average computed on our fleet, is quite high. Moving forward, why energy intensive industry should or could look at energy efficiency? Well, because energy efficiency, and here I'm quoting the International Energy Agency, can be considered the first fuel, let's say, to power our industries, being clean and in most cases also cheap way to meet energy needs. Instead of finding new energy which is cleaner, the first thing that we could look at is to reduce our energy consumption. And in the past few years, we have seen, let's say, a bit of literature about what is Scope 1, Scope 2, and Scope 3 emissions reductions, depending on the fact that certain process can reduce directly or indirectly the emissions associated to the process itself. When we talk about waste heat recovery in industry, usually we are in between Scope 1 and Scope 2, let's say, emission savings. And so this is, let's say, what we will see through some examples today. But what about the competitiveness, the possibility to implement such waste heat recovery projects in a sustainable way, not just from an environmental point of view, but also from an economic point of view? Because of course, this is, let's say, an important aspect, probably still the most important aspect that industries are looking at. Well, depending on the type of application that we are looking at, but usually this is quite typical for waste heat recovery, the levelized cost of energy that I have producing electricity by means of an ORC-based heat recovery system could be as low as 30 to 50 euros per megawatt hour, which is actually a value that is let's say, competitive against other renewable energies, for example, such as PVs or wind. Of course, waste heat recovery from a continuous process, has the big advantage of being base load, basically, which is something that other renewables cannot be, because of course solar and wind are not always present. At the same time, if we look at the avoided CO2 that a waste heat recovery project can bring in terms of reduction of CO2, and we compare this reduction to the cost of my system, we can see how what we could call levelized cost of CO2 reduction is comparable or even lower than what is our carbon tax nowadays, being this cost of CO2 reduction in the range of 25 to 40 euro per ton of CO2. So if we look at the economic numbers that this type of project can create, we can say that there are the numbers to be, let's say, competitive and interesting. Moreover, today, where we, let's say, in a period of, let's say, great instability for what concerns energy supply and security and energy cost. So how this type of industries, of energy intensive industry, can look at these projects? Here we have, let's say, we are highlighting 4 main sectors, which are also the ones that we know better, having developed and built several plants in this type of industries. Of course, these are not the only ones that can be considered. It is a matter all the time to understand what are the typical characteristics of the waste heat available in order to, let's say, assess the possibility to do waste heat recovery through organic Rankine cycle technology. So let's say here we have industrial processes. Here we can say that, as I anticipated, we have also waste heat recovery from other power production technologies, such as gas turbines running open cycle, as well as gas engines working again open cycle, or at least not in CHP mode, which may be something that can be found in some facilities that have their own power plant producing power for their own consumption. And so let's see now, let's have a closer look at the oil and gas industry, the petrochemical industry. And here we will see, let's say, a few examples on where organic Rankine cycle technology could be applied. We cannot cover, of course, all the possible cases. This is just something to give you some example or ideas for where it could be applied as a technology. So if we look at the oil and gas industry, let's say it is a quite big sector, let's say, with many processes involved all over the place, upstream, midstream, and downstream. For, let's say, to simplify a bit the discussion, we have identified three main families of waste heat recovery application within the oil and gas industry. The first one is related to gas compressor stations, which is a facility that is pretty common along all the natural gas pipelines, as well as gas storages or gas, let's say, processing facilities. Here, for this specific application, we're talking about waste heat recovery from open cycle gas turbines, which is something that, let's say, is still quite common. Maybe, let's say, now we are, let's say, we would think that electric motor driven compressor are the most common solution for this type of facilities. It is a yes and no. There are still many that operate open cycle gas turbines or reciprocating engines. And this is the first family we can identify. We have another one connected to processing facilities, such as refineries or petrochemical complexes. Here, let's say, we have a word, meaning that there are many different processes that we can find all throughout the supply chain. So it is a bit difficult to identify some specific application that could be representative. But in any case, what we can say is that there are many processes that happen at high temperature, medium temperature, and that have waste heat streams that are currently cooled down by means of trim coolers, aerial coolers. Of course, where we have some cooling, that means that we are dissipating thermal power. What we can consider is to see if an organic Rankine cycle could be used instead to do that cooling in order to take advantage of the waste heat that is available, and at the same time reduce the cost of cooling, which is in place nowadays, because we are consuming power to run these aerial coolers, for example. And Bamboo project was focused in Bamboo refinery Tupras refinery in Izmir to analyze in depth this type of application. Last but not least, the exploitation of the so-called associated petroleum gas, which is more commonly named flare gas. In this case, it is just a matter of using the thermal power coming from the combustion of the flare gas to feed an ORC unit and to produce power. So basically, in most cases, we cannot avoid burning this associated gas, which is a byproduct of the extraction process. But at least we can take advantage of the thermal power released by this type of gas. A couple of examples. So I think the idea is pretty clear. Wherever there is a waste heat stream, we can evaluate if there is potential to do waste heat recovery or not. In the case of Tupras Izmir refinery, we evaluated to use the atmospheric residue of the crude distillation unit to feed an ORC unit. And the result was that a potential 2 megawatt ORC unit could be installed in the facility, running pretty much all around the year, and over these 8,500 hours of operation throughout the year, this plant would have allowed to save around 7,500 tons of CO2 per year. Of course, reducing at the same time the energy bill of the refinery itself. In this case, the ORC unit would have been placed in parallel to the existing trim coolers and aerial coolers to, let's say, double the cooling capacity of this specific stream. And this is so an example of what could be the waste heat recovery in the refineries. As I mentioned, we have another category, which is the waste heat recovery in gas compressor stations. And here there are several configurations that we can consider, depending on the type of compressor station that we are evaluating and the power of the gas turbine involved, and so on and so forth. Here we are showing just a reference case that Turboden is building now in Egypt. This is an existing gas compressor station that a few years ago was identified to be upgraded, let's say, to increase the pumping capacity of gas throughout the facility. In this case, let's say, instead of adding the new open cycle gas turbines to pump the additional gas to the pipeline, the customer has decided to install Organic Rankine Cycle to do waste heat recovery on the existing gas turbines, and with the power produced, basically drive two electric motor driven compressors that in fact added the new capacity to the station. So in this case, the project is quite big because we are supplying two 12 megawatt each Organic Rankine Cycle turbines. So the numbers, of course, in terms of reduced gas consumption at the facility and the resulting CO2 savings are rather important numbers, but this is, of course, given by the size of this specific project. So basically, we are saving almost 200 gigawatt hour per year of electricity, allowing a saving of gas of around 65 million standard meter cube, and resulting in 120,000 tons of CO2 not emitted every year. Just to give you, let's say, an idea of some numbers about a 5 megawatt project in a gas compressor station, working steady state 40,000 hours per year with some, let's say, boundary conditions that are more related to Europe. We have some, let's say, investment numbers and sensitivity on the results of this possible installation. In the red boxes, there are highlighted the possible results in the current European condition, where the value of ton of CO2 is around 80 euros per ton on the ETS market, and where the electricity price is, let's say, 80 to 100 euro per megawatt hour. Probably this is not, let's say, what we are seeing right now, but hopefully we will be back there in a while. So basically, you see how these figures can be definitely of interest if we want to look at the investment just from an economic point of view. On top of this, of course, we have all the environmental benefit that a project in waste heat recovery can bring. So with this, I have concluded, let's say, the section about waste heat recovery in the oil and gas. I will let the floor to my colleague Mirko, which is here beside me. I guess we can just switch the laptop.
So thank you, Tommaso, for your presentation up to now. I am Mirko Ferrari, and I work as sales engineer in Turboden for the waste heat recovery application in industrial applications, so mainly in the energy intensive industry like glass, cement, and steel. So right now, as Tommaso was mentioning, we are seeing a skyrocketing electricity price through whole Europe in the last year. And in this scenario, also taking into account the attitude of the European state towards the transition to a cleaner energy production, in this situation, heat recovery from industrial processes becomes really a key factor to the reduction of the energy-related cost, but also to the increase of the plant energy efficiency. This is true in almost every sector, so not only in cement, glass, or steel. So as Tommaso was mentioning before, we are several references in these type of industries, and in particular in industrial application, we have right now 35 plants in operation, and 5 of them are currently under construction. Here, just a list of some references for each type of industry. So for instance, we have references in cement plant production, one in Morocco, which is a 2 megawatt plant, up to one in Turkey of 7 megawatt plant. We have some references in the glass industry. Typically, plants in glass industries are lower in size compared to the one of other industries because the conditions, so the let's say the exhaust gas flow rate is lower compared to the one of other application. But we will see also later that we have Tutsicam, which is our biggest ORC plant in glass, which produces up to 7 megawatt of gross power output. And then we have also some references in the steel production industry, starting from a unit near our offices in Brescia, which has a capacity of 700 kilowatt of gross power production, up to Arvedi, which is our biggest unit in steel, which has the power production of 10 megawatt. Here, starting with Arvedi. Arvedi is the biggest electric arc furnaces in Europe, and it has a capacity of 250 tons per day of steel. One peculiarity about Arvedi is that it is the first steel industry in the world that in July 2022 reaches the net zero emission, and it gets the certificate starting from September 2022, and this is also thanks to the presence of our ORC unit installed there. It is a 10 megawatt ORC unit in operation since 2018. It uses saturated steam as a thermal vector from the electric arc furnaces, and this is a very particular example of the flexibility of the ORC unit, as Tommaso was explaining to you before, because typically electric arc furnace process is not stable. It is composed of 2 main stages, power on and power off. And typically you get the thermal power during the power on, so when the metal is melted, and then during the power off, when the metal scrap is charged back to the foundry, typically you don't get thermal power because the furnace is off. And therefore we have this steam buffer upstream the ORC, which takes the steam during the power on and then delivers part of it during the ORC while keeping the remaining part to the buffer itself in order to use it during the power off. And so this allows the ORC to be less dependent from the variances of the thermal power input, and so be the efficiency more constant during the production of the year. Instead, we have a reference in Turkey for Çimkonarlı in a cement plant. And this was the first ORC plant installed in a cement plant in Turkey. And mainly this decision was taken thanks to the fact that, as Tommaso was mentioning before, the ORC plant is very independent from the process upstream. And also because there is, in this case, for instance, the solution is an air-cooled one, so there is no water consumption on site. And this is a very important topic in such a region where water scarcity is a problem and will be a problem also in the future. For instance, in this plant, we have 7 megawatt of gross power production, and this particular plant is in operation since 2019. In this case, and almost in every case of industrial application, the heat carrier is thermal oil because it allows a higher efficiency of the RC unit because typically it can reach higher temperature compared to steam at the same pressure. Here instead we have another references. This one is in the glass industry for Dutzekam. This plant is also in Turkey, and as I was mentioning before, it is a particular size of an ORC for a glass plant because it was designed for two production line of 600 tons per day of flat glass. And nowadays, since it has been a bit oversized, nowadays they are planning to install a third line of additional 600 tons per day of glass. And so they will saturate the potentiality of the ORC, producing up to 7 megawatt per 7 megawatt gross of power output. As I was mentioning, typically the size of the ORC in glass application is below 2 megawatt, generally from 700 up to 1200 megawatt of gross power output. Here we have an example of the economics, in this case for an 8 megawatt ORC plant in a cement plant with a capacity of 5,000 tons per day of kiln. And there are also some assumptions, as in the previous case in the oil and gas. So we are considering 7,500 operating hours per year, and with a weighted average cost of capital of 2%. According to this number, we can see that in this type of cement plant, typically the ORC power range ranges from 7 up to 8 megawatt gross, depending on several factors like the exhaust gas temperature, like the fact that you are recovering both from preheater or from the clinker cooler, and also on the average ambient temperature of the site. For an ORC plant of this size, we can assume a capex of about 3.5 million euro per megawatt hour produced, with an OPEX which is typically 1.5% of the capex. So it will be like 1.8 million euro per megawatt. And a CO2 saving of about 40,000 tons of CO2 per year, according to the 250 kilograms of CO2 per megawatt hour, which is an average emission calculated in the power generating sector. So as before in the oil and gas example, we run a sensitivity analysis according to this data, and we can see that nowadays in Europe, considering the an average of let's say 90 euro per megawatt hour of electricity cost and 80 euro per tons of CO2 emitted as a carbon tax, we can have a payback time of this size of plant, which is below 5 years, let's say 4 years at most. But this is considering, let's say, a relatively low energy price, because nowadays we are foreseeing energy prices which is 3 times this one. It will be lower in the future, hopefully, but we don't think that it will reach again the level before the pandemic and the crisis itself. So to sum up, let's see some guidelines to assess the potential for waste heat recovery in order to understand which are the main parameters to look at when you want to discuss the installation of such a plant in your system. So the good feasibility, typically if you have a high efficiency of the thermodynamic cycle, which means that you have a high temperature of the waste heat sources, or low temperature of the cooling sources. With high temperature, we typically mean at least 300 degrees C at least 3 megawatt thermal available of your heat sources. And with low temperature, you are typically considering an average ambient temperature for European countries, which is around 20-25 degrees C of ambient temperature. Then large amount of thermal power available, and this will lead to bigger plant, and so thanks to the economy of scale, it will result in a lower cost per kilowatt installed, because typically we can produce different ranges of power output using the same unit, but of course larger will be the power input available, and the larger will be also the power output using the same unit, and also with the same cost you will have a lower cost per kilowatt. Then another parameter to be taken into account is sometimes it is one of the most important ones, is also the ease of installation, because ORC units are typically large units, and so you will have to have also the space available on your site in order to install this unit without any too much complexity. On the other hand, the challenging feasibility, if the efficiency of the thermodynamic cycle is low, so if the temperature of your heat source is low, or if the temperature of the ambient, let's say, is too high, then it will result in a very low efficient cycle, and so high, let's say, specific cost for kilowatt produced, and also, of course, complexity of installation. So if the spaces available are very strict and it's very complex to install the unit, it will be a problem since the unit is big, and typically there is nothing that you can do to fit the unit in a small place. So to sum up, the ideal project consists of having the temperature of the heat source above 350, and so our thermal vector above 300 degrees C. Of course, the higher the better, because higher temperature will result in higher efficiency. Then thermal power available from the heat source above 18 to 20 megawatt. This is true for the medium-size plant. Instead, for lower size plant like biomass, typically we can also reach good efficiency with 3,000, 4,000 megawatt of thermal power available, because in general the temperature of the heat source is much higher than 350, so it reaches about 700 to 800 degrees C. And also the ideal project foresees to start from zero, so having ideally all the space required without any constraints, and also high availability of the heat source, because as Tommaso was mentioning, being able to operating at base load condition will increase the amount of operating hours per year, and so reducing the levelized cost of the electricity, which is, let's say, the minimum price at which you should sell the electricity to the market in order to offset your entire investment cost for the production of the plant and also operation of the plant itself. On the other hand, having the temperature source at low temperature, so below 200 degrees C, and too low thermal power, below 4 megawatt, does not allow you to get good efficiency, and so it will cause your levelized cost of electricity to be too high to be technically, but also economically feasible, and justify an investment of one of the ORC units. So with this, I hope that we cleared many of the doubts that we have about the ORC plant. I hope that now the technology is more clear to you, and feel free to ask anything that you may have not clear yet to us. And I would like also to thank again the organizers of this webinar to allow us to have the opportunity to present our technology to you all, and thank you all to the participants.
Thank you, Mirko and Tommaso. Very encouraging figures in a time of sobriety. Now we'll take questions from the audience. There are plenty. I don't know if we'll have the time to answer all of them. First one is, what is the smallest system size that Turboden supplies in metric million British thermal units?
Okay, I mean, I don't have the answer in British thermal unit since I'm not very used to it, but if you can, let's say, I can reply, let's say, in kilowatt, let me say. So if we look at the electrical production, our smallest ORC unit is rated 700 kilowatt electric power output, which means around 2.53 megawatt of thermal power from the heat source at high temperature. There are also, let's say, other manufacturers that can provide also smaller units, but this is not, let's say, covered by Turboden. So our portfolio of products starts from 700 kilowatt of electric power output.
So there is a question now that I don't know if the answer was already included in the last slide, but I'll tell you. What are the main characteristics that a project must have to include the regenerator in the ORC system? All right. So basically, the regenerator is a component that allows to recover heat after the vapor has expanded in the turbine. Typically, in high temperature applications, there is the regenerator because this helps increasing the efficiency of the thermodynamic cycle. While in low temperature applications, there is like geothermal application, for example, and there is no use of the regenerator since the entire system is working at lower temperature. So there is no need of this specific component. But let's say it is a design choice that we make every time in order to optimize the overall solution. So, but generally high temperature, then we have the regenerator. Low temperature application, then we do not have the regenerator. So this is an interesting question. Are ORC systems suitable for island operation? It is possible, of course.
This is something related to the electrical architecture and the infrastructure. So let's say it is a possibility. It is just a matter of knowing that island mode operation is required and the system can be designed for this type of operation. We have a few plants working this way. The one that was showing in Egypt will work in island mode. Of course, there are some costs associated to this type of operation, because there are usually some additional components required on the electrical infrastructure in order to be capable to sustain the island. So there will be a load bank and some specific design choices on the ORC unit to make the ORC suitable for this type of application. But as Turboden, we already provided plans working in this way, and so we do also have the expertise to do this.
Okay, what is the temperature level of the waste gases for the application of ORC?
So let's say, as mentioned by Mirko at the end of the presentation, the higher the better. Let's say if we have to put a minimum on exhaust gas, I would say 250, 300 degrees C. And this is not, let's say, a technical limit, but mainly an economic limit, because let's say you can do waste heat recovery from exhaust gas at 200 degrees C, at 150 degrees C also. But let's say then you need a very big heat exchanger to catch that heat, and let's say the efficiency of the ORC cycle at the same time will be necessarily lower, because lower temperature of the heat source means also lower thermodynamic efficiency of the cycle. So at the end of the day, okay, from a technical point of view, you can do it, but there is, let's say, there are some challenges for what concerns the economic viability of such a kind of application. So I would say, if we are talking about exhaust gas, at least 250. Then if we look at liquid type heat sources, in that case, the basically the heat capacity of a liquid stream is typically much higher compared to a gaseous stream, and so in that case we can go lower, and in fact all geothermal applications that we have run with hot water from the underground around 120 to 140 degrees C, something like that.
Okay, now the next question is quite long. Currently, our cement industry is using steam-based Rankine cycles for waste heat recovery-based power generation. Very limited cement plants are using Kalina cycle-based waste heat recovery systems for low-grade waste heat recovery. Is it feasible for cement industry to install ORC-based waste heat recovery system, although steam-based Rankine cycle is unable to recover low-grade heat, but isn't it more efficient than ORC? Aha.
I'm not sure if I got the question right. I tried to answer. So let's say Organic Rankine Cycle is capable to work both at high temperature as well as low temperature. What we do time by time is to select a different working fluid according to the temperature of the waste heat source that we have available. So for high temperature application, we use hydrocarbons. For low temperature application, we might use other type of hydrocarbons or refrigerants. So generally speaking, we can adapt both to high temperature application as well as low temperature application. So wherever there is a steam cycle doing waste heat recovery in cement, well, that case is suitable also for organic Rankine cycle. It is just a matter of understanding how big is the plant, what are the figures of steam turbine, and compare them to an organic Rankine cycle turbine, which could be, let's say, quite aligned. But both choices, let's say, are available. When you go to low temperature application, usually steam turbines suffer a bit in terms of efficiency. You might have some problems, let's say, in terms of evaporating pressure and temperature of your steam. So you might not be able to reach the ideal conditions of the steam entering the turbine. And so in that cases, I presume that an organic Rankine cycle could be always a better choice. Kalina cycle, I'm not sure how many plants are in operation with this type of cycle, which we don't see very often, to be honest, on the market. So I cannot really tell if it is a well-established technology or these are mostly pilot plants that have been built. On this, I'm not sure. But generally speaking, organic Rankine cycle is suitable for both high temperature and low temperature. Of course, this is thermodynamics, unfortunately, that is telling this. If the temperature is lower, the efficiency of the cycle will be physiologically lower. But this is again thermodynamics.
Okay, so I think we have one last question that can fit in. The prices of 30 to 50 euros of megawatt hour generated were based on the prices of projection systems of 2018 to 2019, etc. Okay, and compared to inflation of prices of everything of nowadays, how would it be the prices of cost of the energy generation? So how would it compare with today?
Okay, let's say, of course, this inflation has affected everybody. We have seen increase of raw materials cost and everything. So there will be a slight increase of these levelized cost of energy, which in any case is lower compared to the steep increase that the energy had in the past 12 months, I would say. So let's say the current period is considering the current prices of electricity are, let's say, even more favorable, let me say, for the application of this type of technology, because it is true that maybe the LCOE is a bit higher compared to a couple of years ago, but still on the other end, the energy price has increased much more. So this is something to take into consideration. Also, let me say that the figures that we have provided are, let's say, are high-level figures that should give an idea of what is a possible target. Of course, we are talking about quite big projects with many components that come together with specific features of the site that change from one side to the other. So keep these numbers as, let's say, a high-level indication. But of course, let's say, every project has its own history, let me say, and features, so that maybe a project is particularly lucky, let me say, which is, let's say, and this might help more than what we have seen in inflation.
Okay, so our time ends here. Thanks a lot, everyone. I'm sorry for the people who asked more questions. It's nice to see there's a lot of interest. And I'm also sorry you couldn't see my face, but as I said at the beginning, I had issues with my connection, so please forgive me. And I remind you that the next webinar of the series will take place next Wednesday, November 9 at the same time, 3 p.m. Central European Time. And we will talk about fuel flexibility in combustion processes in energy-intensive industries. I hope to see you there. So have a great afternoon. See you soon. Bye.
Thank you. Thank you, everybody.
Thank you, everybody. Bye.
Thank you.